Ever wondered how AI systems simplify complex data? A key player in this process is the concept of eigenvalues and eigenvectors. Let's start by picturing a bustling city. Now imagine trying to navigate through this city without a map. Pretty daunting, right? This is similar to how an AI system feels when it's faced with a complex set of data. It needs a map, a guide to understand it. That's where eigenvalues and eigenvectors come in. Eigenvalues and eigenvectors are essentially the compass and map for AI systems. They guide the way through the complex landscape of data, pointing out the most important features and helping to simplify the journey. But what exactly are they? In the simplest terms, an eigenvector is a direction. In our city analogy, think of it as the north, south, east, or west. It's a direction in which our data is spread out. An eigenvalue, on the other hand, is a number that tells us how much variance there is in the data in that direction. It's like knowing how long a city block is. These might seem like abstract concepts, but they play a crucial role in many areas of mathematics and AI. They are used in systems that recognize faces in a crowd, recommend your next favorite song, or even predict stock market trends. These concepts are not just confined to AI, but are also fundamental in physics, where they help in understanding quantum mechanics and in engineering for stability analysis, to name just a few applications. So why are these concepts so important? Well, they allow AI systems to transform complex, high-dimensional data into a simpler, lower-dimensional form. This transformation makes the data easier to understand and work with, much like how a map simplifies a bustling city into an easy-to-read layout. In essence, eigenvalues and eigenvectors are mathematical tools that AI utilizes to make sense of large, complicated datasets. Now that you know what eigenvalues and eigenvectors are, you might be curious about how to find them. Well, sit tight as we unravel this mathematical mystery together. To find the eigenvalues of a matrix, we must first understand what it means for a vector to be an eigenvector. An eigenvector of a matrix is a non-zero vector that, when the matrix is applied to it, does not change direction. Instead, it's scaled by a factor, the eigenvalue. Let's take an example of a simple 2x2 matrix. To find the eigenvalues, we subtract a variable, usually denoted as lambda, times the identity matrix from our original matrix. This results in a new matrix. The determinant of this matrix set equal to 0 gives us the characteristic equation. Solving this equation for lambda will give us our eigenvalues. Remember, a matrix can have 1, 2, or more eigenvalues depending on its size. Now, on to finding the eigenvectors. Once we have the eigenvalues, we substitute each one back into the matrix we obtained by subtracting lambda times the identity matrix. This gives us a system of linear equations. Solving this system for each eigenvalue will give us our eigenvectors. It's important to note that the eigenvector isn't unique. Any non-zero scalar multiple of an eigenvector is also an eigenvector. But for simplicity, we usually normalize them, meaning we scale them to have a length or magnitude of 1. As you can see, finding eigenvalues and eigenvectors involves a bit of algebra, a touch of calculus, and a healthy dose of curiosity. But don't worry if it seems a bit complex at first. Like any good detective story, the more you delve into it, the more the plot unfolds, and the clearer everything becomes. And there you have it, a step-by-step guide to finding eigenvalues and eigenvectors, the silent heroes behind AI's data simplification. But wait, there's more! Let's dive into the magical world of matrix diagonalization. Matrix diagonalization is like a magic trick that can transform a complex matrix into a simpler, more manageable form. This transformation is not just for aesthetics. It's a powerful tool that can simplify complex problems in fields such as artificial intelligence. So what is matrix diagonalization? Imagine you have a square matrix. The goal of diagonalization is to find a basis in which this matrix is diagonal. A diagonal matrix is one where all elements outside the main diagonal are 0. This makes computations, such as raising the matrix to a power, much easier. Let's illustrate this with an example. Suppose you have a matrix and you've already found its eigenvalues and eigenvectors. Now you can form two new matrices. The first one, let's call it P, is formed by placing the eigenvectors in columns. The second one, let's call it D, is a diagonal matrix formed by placing the eigenvalues along the diagonal. Here's the magic part. If you multiply P by D, and then by the inverse of P, you get back the original matrix. This transformation is known as diagonalization, and the matrix P is called the change of basis matrix. But why does this matter? Well, diagonalization can be a real game changer in AI. For example, in machine learning, we often deal with high-dimensional data that can be hard to manage. By diagonalizing the covariance matrix of this data, we can reduce its dimensionality, making it more manageable and easier to analyze. It's also worth noting that not all matrices can be diagonalized. A matrix is diagonalizable if and only if it has a full set of linearly independent eigenvectors. But when it is possible, diagonalization is a powerful tool that can simplify complex problems and reveal hidden structures in data. Matrix diagonalization is a powerful tool that can simplify complex problems in AI. So, how do these mathematical concepts fit into the grand scheme of AI? Let's uncover the role of eigenvalues, eigenvectors, and matrix diagonalization in principal component analysis and dimensionality reduction. Principal component analysis, or PCA, is a statistical procedure widely used in the field of AI. It's a dimensional reduction tool that can be used to reduce a large set of variables to a small set that still contains most of the information. The magic behind PCA? You guessed it. It's all about eigenvalues and eigenvectors. PCA starts by calculating the covariance matrix of the data. This is where eigenvalues and eigenvectors come in. The covariance matrix is symmetric, and symmetric matrices have this amazing property that they can be diagonalized by a basis of eigenvectors. When we diagonalize the covariance matrix, its eigenvalues are the variances of its eigenvectors. The principal components of PCA are these very eigenvectors, ordered by the corresponding eigenvalue. The larger the eigenvalue, the more variance, information, its corresponding eigenvector holds. By selecting the top few eigenvectors, sorted by their eigenvalues, we reduce the dimensionality of our data while preserving as much information as possible. Dimensionality reduction is crucial in AI. High-dimensional data can be a curse, causing overfitting, long processing times, and decreased model performance. By using PCA, we can simplify our data without losing too much information. It's like getting the gist of a long novel by reading a well-written summary. Furthermore, PCA can also help in visualizing high-dimensional data. By reducing dimensions to 2 or 3, we can plot and better understand the structure and patterns of our data. In the world of AI, these mathematical concepts are not just abstract theories, but practical tools that help us make sense of complex data. So next time you're faced with a high-dimensional data set, remember the power of eigenvalues, eigenvectors, and PCA. Before we wrap up, let's summarize the key points we have covered today. We started our journey by delving into the intricate world of eigenvalues and eigenvectors. These aren't just fancy terms. They're fundamental concepts in linear algebra that help us understand the nature of mathematical transformations. Eigenvalues provide us with the scale of transformation, while eigenvectors serve as the axes along which this transformation occurs. Then, we explored how to find these elusive eigenvalues and eigenvectors. We learned that it's not about random guesswork, rather a systematic process involving determinants and characteristic equations. When we solve these equations, we discover the eigenvalues, and by substituting them back into our equations, we unearth the corresponding eigenvectors. It's like a treasure hunt, where the treasure is a better understanding of our mathematical transformations. Our third stop was the magical realm of matrix diagonalization. Here, we saw how a matrix can be transformed or diagonalized into a much simpler form using its eigenvalues and eigenvectors. This diagonalization process simplifies complex calculations and makes them more manageable, much like decluttering a messy room. Finally, we ventured into the practical applications of these concepts in the world of artificial intelligence, specifically through principal component analysis, or PCA, and dimensionality reduction. We saw how PCA uses eigenvalues and eigenvectors to reduce the dimensionality of data, making it easier to handle, analyze, and visualize. In essence, PCA is a way of simplifying our data while retaining as much of the useful information as possible. Remember, behind every efficient AI system, there's a world of complex mathematics simplified by eigenvalues, eigenvectors, and matrix diagonalization. Next time you interact with an AI, spare a thought for these unsung heroes of the mathematical world.